Okay, so today's lecture is about deep learning, and we'll use Spark and H2O AI to show you. I'll show you a demo using H2O AI and Spark which uses deep learning. So first off, credits to other people who have done a lot of work, putting a lot of material together, which I've borrowed. So most of the videos you see on this worksheet and on the others are from this course called Deep Learning. It's on Udacity. It's by Arpan and Vincent. And it's a really good course. They use TensorFlow, and a lot of concepts of deep learning are explained really well, as you'll see in the videos. And then I strongly recommend you to go to this website. It's called Neural Networks and Deep Learning by Michael Nielsen. It's a really nice introduction to deep learning. It'll probably take like 1 or 2 days to go through the different pages. So he's used the handwritten digits example that we saw before, sometime before. This was the handwritten digits data was collected by Jan LeCun, who was one of the pioneers, I guess, in deep learning. So please go through this website. It has a lot of good stuff. And some of the images from our lecture are also borrowed from this website. Also do go through this book called Deep Learning Book. So this is written again by Joshua Bengio, Ian Goodfellow, and Aaron Corwell. So these guys are again really famous guys in deep learning. So this book is going to be published by MIT, but the whole content is available to you for free online, and this will remain free online. So yeah, this is a really good method. And the good thing with this book is not only do they cover the basics of deep learning, like basics of linear algebra probability, but also go through the current deep learning scenario with feed-forward networks, convolutional neural networks, and also they have content about the research areas that are currently being pursued by different people in deep learning, like AutoEncoders and Monte Carlo methods and so on. So it's a good book for people. So I think one of the websites somewhere that it mentions that this book is good for people in software engineering who want to get introduced to deep learning. So it'll start right from the basics that you require, go through the current scenario in deep learning, and also go through the research available. Right? So what is deep learning? So deep learning is actually a buzzword, I guess, for artificial neural networks. And artificial neural networks have been in play since the 1960s. For a long time, there was a lot of excitement in artificial neural networks, and then it died down, and then there was again a revival, and then it went down. And now with deep learning, it's taken on a whole new level. So what it does, what is deep learning? So there are two things that you can do with deep learning. You can use it as a supervised learning model, where you can use it as a classifier, and as an unsupervised model, you can use it for anomaly detection. As a supervised learning model, we'll go through fully connected networks, convolutional networks, and recurrent neural networks. But the thing with deep learning is that it needs lots and lots of data, right? So only if you have a lot of data, you can use deep learning. Otherwise, it doesn't perform very well. The other good thing with deep learning is that it's an online training model. So if you already trained your model using some data that you have, and you get a new data point or set of new data points, you don't have to rebuild your whole model. So that's a big advantage of deep learning over other classification methods, let's say like linear logistic regression or SVMs and those things. And then of late, there are these techniques that have become quite popular called dropouts, and we'll see a really good video about dropouts. And for regularization, dropout is one of the techniques. There are other techniques like L1, L2 regularization, which I think people are familiar with. Okay. So why these models? Fully supervised learning has these three models, as I said before. So The fully connected network is what you'll normally use for classification. If your data is image data, the recommended supervised learning technique is convolutional neural network. We'll see what that is. And then for text and speech or time-based data, let's say, we use recurrent neural networks. And for unsupervised learning, for anomaly detection, there's a technique called AutoEncoder. So before we get into deep learning, let's quickly recap linear models, just so that we can contrast deep learning with the other popular techniques. So I'll play this video. This is again by Vincent.
The logistic classifier is what's called a linear classifier. It takes the input, for example, the pixels in the image, and applies a linear function to them to generate its predictions. A linear function is just a giant matrix multiplier. It takes all the inputs as a big vector that will denote x, and multiplies them with a matrix to generate its predictions, one per output class. Throughout, we'll denote the inputs by x, the weights by w, and the bias term by e. The weights of that matrix and the bias is where the machine learning comes in. We're going to train that model. That means we're going to try to find the values for the weights and bias which are good at performing those predictions.
Okay, so this is the logistic classifier that we know. So the same thing, if you look at it in this diagram, so let's say the blue points are your data points, which are, let's say, x and y values, which are plotted here, and the red line is our model, for example. So this is a really oversimplified model. We are just using a straight line here, but even the logistic classifier doesn't do that. But just for understanding, let's say we have this red line as our optimal model. Now what we're trying to do is, from each of these points, let's say we drop a vertical line onto the red line. So that is the cost of each point, right? So that, and we sum the squares of these costs and we try to minimize the cost. So we have a bunch of points and we're trying to fit a line through these points, right? And the way we fit this line is that we take the actual value that the point says it is, and the value which the line thinks that the point should be, okay? So we take the actual value and the value predicted by our function, and then we take the sum of squares and try to minimize that, okay? So that's the optimization we are trying to perform here. So here, let's say y is mx plus c is the line that we are trying to plot, and this is what we're trying to do, okay? Now, another way of looking at the same model is this. So let's say we have three inputs, x1, x2, x3, or let's say let's just ignore x3 for now, and let's just say we have x and y as inputs. What we're trying to learn is the weight on each of these edges. Okay, so for some value of x1, okay, so x1 into some a plus let's say x2 into some b, okay, that will give you the output, okay, and we are trying to minimize that particular cost, okay. And the reason I'm showing you this image now will become clear when we go further down. Okay? So the way we optimize that and the way we try to reduce the cost is through gradient descent, okay. So I'll play this video, again done in the Udacity course.
Okay, so now we have all the pieces of our puzzle. The question, of course, is how are we going to find those weights W and those biases B that will get our classifier to do what we want it to do? That is, have a low distance for the correct class, but have a high distance for the incorrect class. One thing you can do is measure that distance averaged over the entire training set for all the inputs and all the labels that you have available. That's called the training loss. This loss, which is the average cross entropy over your entire training set, is one humongous function. Every example in your training set gets multiplied by this one big matrix W, and then they get all added up in one big sum. We want all the distances to be small, which would mean we're doing a good job at classifying every example in the training data. So we want the loss to be small. The loss is a function of the weights and the biases. So we're simply going to try and minimize that function. Imagine that the loss is a function of two weights, weight 1 and weight 2.
Let me just pause here. So this diagram you see is of concentric ovals, right? So actually what this is called a contour plot. Okay, so we see weight 1 and weight 2 on the X and Y axes. So imagine that you're trying to fit a line with two parameters, right? Y equal to mx plus c. So for different values for m and c, the loss will either be large or it'll be small, right? So for different values of m and c, you'll get different values as the the loss function. So when you plot the output, the loss against the inputs m and c, what you'll see is you'll find a graph like a bowl, right? Because at the optimum value of m and c, it will be minimum, and at different values it will be more than that. And what this is just a projection of that. So these contours, these two different circles, right? What they represent is the difference in height between each subsequent things, right? Okay.
2. Just for the sake of argument, it's going to be a function which will be large in some areas and small in others. We're going to try to find the weights which cause this loss to be the smallest. We just turned the machine learning problem into one of numerical optimization. And there's lots of ways to solve a numerical optimization problem. The simplest way is one you've probably encountered before, gradient descent. Take the derivative of your loss with respect to your parameters and follow that derivative by taking a step backwards. Then repeat until you get to the bottom. Gradient descent is relatively simple, especially when you have powerful numerical tools that compute the derivatives for you. Remember, I'm showing you the derivative for a function of just two parameters here. But for a typical problem, it could be a function of thousands, millions, or even billions of parameters.
So you take the function, you take the derivative of the function, the derivative of the loss function, which will tell you the direction in which you need to take the next step, okay? Because you want to get to the bottom of your function, right? So you know the function you want to optimize, and the derivative will tell you the direction in which you need to take the step. And this alpha is called the step size. So it will tell you how big a step you need to take so that you get to the bottom, right? So why we need this alpha is, let's say we are already at the bottom or very near the bottom, and then the derivative will still tell you in which direction to step. But if the alpha is too big, you'll actually overshoot, right? So you'll keep going back and forth. So you need to make sure that your alpha is also optimized. And there's a way to do this automatically, and we'll see that. Okay. Now this is a variation of gradient descent, which is called stochastic gradient descent. And this is the one that's used by most machine learning libraries, and the reason will become clear to you.
The problem with scaling gradient descent is simple. You need to compute this gradient. Here's another rule of thumb. If computing your loss takes n floating point operations, computing its gradient takes about 3 times that compute. As we saw earlier, this loss function is huge. It depends on every single element in your training set. That can be a lot of compute if your data set is big. And we want to be able to train on lots of data, because in practice, on real problems, you'll always get more gains the more data you use. And because gradient descent is iterative, you have to do that for many steps. That means going through your data tens or hundreds of times. That's not good. So instead, we're going to cheat. Instead of computing the loss, we're going to compute an estimate of it. A very bad estimate. A terrible estimate, in fact. That estimate is going to be so bad, you might wonder why it works at all. And you would be right, because we're going to also have to spend some time making it less terrible. The estimate we're going to use is simply computing the average loss for a very small random fraction of the training data. Think between 1 and 1,000 training samples each time. I say random because it's very important. If the way you pick your samples isn't random enough, it no longer works at all. So we're going to take a very small sliver of the training data, compute the loss for that sample, compute the derivative for that sample, and pretend that that derivative is the right direction to use to do gradient descent. It is not at all the right direction. And in fact, at times, it might increase the real loss, not reduce it. But we're going to compensate by doing this many, many times, taking very, very small steps each time. So each step is a lot cheaper to compute, but we pay a price. We have to take many more smaller steps instead of one large step. On balance, though, we win by a lot. In fact, as you'll see in the assignments, doing this is vastly more efficient than doing gradient descent. This technique is called stochastic gradient descent and is at the core of deep learning. That's because stochastic gradient descent scales well with both data and model size, and we want both big data and big model. Stochastic gradient descent, SGD for short, is nice and scalable, but because it's fundamentally a pretty bad optimizer that happens to be the only one that's fast enough, it comes with a lot of issues in practice.
Okay, so that's what we do. We don't take the full data, but we take a random sample of the data, and then we step in that direction, and that's what gives us the optimization. Okay, so instead of doing these steps, say 20 times, we do it, say 100 times. Okay? And stochastic gradient descent is used in most optimization techniques now. Now, this paper, okay, is stochastic gradient descent without locks. Okay. So what H2O AI have done is they've implemented this paper in their framework, and what this provides is, instead of it utilizes the whole cluster to perform stochastic gradient descent, and while doing that, it will not lock the variables. By locking, I mean, let's say you compute the derivative, and then you know which direction to step. Now, if let's say parts of the derivative are computed at different nodes, then you'll need to update one common variable, right? Because one machine says, okay, this is the step that I found, or this is the direction I found. So this particular algorithm will make sure that there are lock-free variables, and it will help you parallelize stochastic gradient descent. So I haven't gone through this paper myself, but it's a good paper. Okay, now that we have spoken all about stochastic gradient descent and linear models, why do we need deep learning? Because linear models already give you good classification techniques, right? So why deep learning?
Also, it's linear. This means that the kind of interactions that you're capable of representing with that model is somewhat limited. For example, if two inputs interact in an additive way, your model can represent them well as a matrix multiply. But if two inputs interact in a way that the outcome depends on the product of the two, for example, you won't be able to model that efficiently with a linear model.
Right, so that's it. That's the difference between linear models and neural networks and deep learning. So if you have different features and you need to build a model, and if these features interact with each other in a linear way or an additive way, then your logistic regression can represent that well in a model. But if it's not linear, if it's non-linear, then your logistic regression cannot do it. It's not that you cannot do it. What you'll have to do is you'll have to hand featureize your features. So you'll need to understand that feature A and feature B are nonlinear and they interact in a certain way, and then you have to derive a feature, so let's say AB dash or something that represents this nonlinearity between A and B. And you have to hand featureize your features. That's what you need to do in nonlinear if you want to use logistic regression. But what deep learning does is it does this automatically. Okay, and that's the big advantage of deep learning. And the way it does this is very simple. It uses this particular function. So ignore the green line for now. Okay, ignore the green line. We are only going to look at this blue line. And if you see what this blue line is, it's nothing but max of 0, x. So whatever input it gets, if it's less than 0 or less than equal to 0, it makes the output 0. And if the value is greater than that, the output is equal to the input. Okay, so it's very simple. All negative values and all zeros are just simply made 0. And this is a nonlinear function, right? And what you do is you take this function and you stick it in between the matrix multiplications, as you'll see here.
Because we're lazy engineers, we're going to take something that works, a logistic classifier, and do the minimal amount of change to make it nonlinear. We're going to construct our new function in the simplest way that we can think of. Instead of having a single matrix multiply as our classifier, we're going to insert a ReLU right in the middle. We now have two matrices, one going from the inputs to the ReLUs, and another one connecting the ReLUs to the classifier. We've solved two of our problems. Our function is now nonlinear, thanks to the ReLU in the middle, and we now have a new knob that we can tune, this number h, which corresponds to the number of ReLU units that we have in the classifier. We can make it as big as we want. Congratulations, you built your first neural network.
Okay. So this is what it looks like. So we have the inputs, right? And then on each of these edges, we learn weights, which is the the matrix multiplication step. And inside this hidden layer, we have ReLUs, okay, which is the nonlinear function. And then these arrows which are coming out of the hidden layer, these also, on these edges also we learn weights. So that's what this is. So this W1 is the set of all weights in this, on these edges. This ReLU is here, and the length of the ReLU, the h, is nothing but the number of hidden units we have, right? And W2 is this one, the weights on these edges. So we have one layer, right? One layer of hidden nonlinear functions, and then we learn weights on each of these edges. And why does this work? We'll see that just a couple of slides from now. And if you take the same diagram and you expand the hidden layer out, and you put in multiple hidden layers, in this case we have 3 hidden layers, right? That is a deep learning network. That's all it is, right? In this image, the hidden layers are shown to be of the same size, but they need not be the same size. And if you have different sizes in these hidden layers, they actually mean something, and we'll see that later, okay? So as you see here, each input layer is connected to every single unit in the hidden layer, right? And the hidden layers themselves are connected to every single unit in the next layer. So this is why it's called the fully connected network, okay? And the output layer will actually be the number of categories or number of classes of outputs that you want. So in the case of handwritten digit recognition, the output would be 10 because you want to recognize numbers from 0 through 9. And the input, because our image size is, let's say 28 by 28, so it will be 28 into 28. So there will be so many input nodes, okay? And how many nodes do we want to keep in this hidden layer? This is again a hyperparameter tuning step, okay? Right. So what do each of these hidden layers mean? Okay, why do we need so many hidden layers? What is the functionality that each hidden layer brings? Okay.
So now you have a small neural network. It's not particularly deep, just 2 layers. You can make it bigger, more complex, by increasing the size of that hidden layer in the middle. But it turns out that increasing this h is not particularly efficient in general. You need to make it very, very big, and then it gets very hard to train. This is where the central idea of deep learning comes into play. Instead, you can also add more layers and make your model deeper. There are lots of good reasons to do that. One is parameter efficiency. You can typically get much more performance with fewer parameters by going deeper rather than wider. Another one is that a lot of natural phenomena that you might be interested in tend to have a hierarchical structure which deep models naturally capture. If you look at a model for images, for example, and visualize what the model learns, you'll often find very simple things at the lowest layers, like lines or edges. Once you move up, you tend to see more complicated things like geometric shapes. Go further up, and you start seeing things like objects, spaces. This is very powerful because the model structure matches the kind of abstractions that you might expect to see in your data. And as a result, the model has an easier time learning them.
Okay, so that's what each of the subsequent layers do. They see if we let's say hide this input layer itself, then the input to hidden layer 2 is actually hidden layer 1, right? So what each layer is doing is it's learning more and more abstractions. So the first layer learns, let's say, edges in an image. The second layer learns some kind of shapes. And the third layer puts everything together and forms some kind of an image. So each layer is learning higher and higher abstractions of your input data source. Okay. And the way it does this is through something called back propagation. So that is the way it learns the weights on each of these edges, which is the important part, right? That is through an algorithm called back propagation. But before we get to back propagation, we need to understand something called the chain rule, which which I think we've learned it in high school, I guess. So I'll just play this video.
One reason to build this network by stacking simple operations like multiplications and sums and values on top of each other is that it makes the math very simple. Simple enough that a deep learning framework can manage it for you. The key mathematical insight is the chain rule. If you have two functions that get composed, that is, one is applied to the output of the other, then the chain rule tells you that you can compute the derivatives of that function simply by taking the product of the derivatives of the components. That's very powerful. As long as you know how to write the derivatives of your individual functions, there is a simple graphical way to combine them together and compute the derivative for the whole function. There is even better news for the computer scientist in you. There is a way to write this chain rule that is very efficient computationally with lots of data reuse, and that looks like a very simple data pipeline.
Okay, so we use the chain rule to compute the derivative of this full big function, right? Okay. So once you get the derivative, all we need to do is use the stochastic gradient descent, right? Because you know the derivative of the full big function, and then you plug it into stochastic gradient descent, and that function gets optimized, and then you get the values for each of the each of these edges. Right? So what back propagation is that you it's closely related to dynamic programming. So it's like you know what the output should be, you know how the output is connected to the input. Okay, so if we look at this, okay, this output, okay, to get this output, it needs to have some value on this edge and some value on this edge. So it's actually connected to all these nodes, right? So given some input, some set of inputs, okay, and you know what the output should be, and you know how these are connected to each other, then what should these previous step, what should be the value on these previous edges so that you get that in? So that's how it works. Okay, so what it does is, if you watch this video, it will help you understand it much more clearly, but I won't play this video now. So what it does is, let's say we have two variables, let's say x1 and x2, okay, and the function between them here, okay, let's say x1, x2, and the function that joins them, let's say, is a multiplication, okay. Here it's plus, but let's say this is multiplication. So in this sense, let's say this is x1, x2, and let's say this is multiplication, and then you have the output. If x1 increases by 1, right? If x1 increases by 1, what do you think will happen to the output? Right, it will increase by x2, isn't it? It'll increase by x2. So let's say 3 and 4. Okay, let's say x1, x2 are 3 and 4. So 3 4s are 12. Now if the 3 becomes 4, the output is 16. So it has increased by x2, right? So use the same trick and do it in the reverse. Okay, so the output is some, say, the output here, let's say this output is 1 and all these outputs are zeros. That means, let's say it's category 1. And so if this has to be 1, then these have to be some values, right? And if this has to be 1 and these have to be 0, all of these edges have to be some values. So you go back. Okay, that's what back propagation is. And you see these values here. Okay, so these are the intermediary values for each weight in this edge. Okay, in this edge, each edge has some weight depending on each of the inputs that it receives. And then when it gets a new input, it will recalculate the weights on those edges. Okay, so if you should definitely watch this video. It talks about back propagation without using any derivatives. Okay, and this is Vincent's explanation of back propagation.
Here's an example. Imagine your network is a stack of simple operations, like linear transforms, ReLUs, whatever you want. Some have parameters, like the matrix transforms, some don't, like the ReLUs. When you apply your data to some input X, you have data flowing through the stack up to your predictions Y. To compute the derivatives, you create another graph that looks like this. The data in that new graph flows backwards through the network. It gets combined using the chain rule that we saw before and produces gradients. That graph can be derived completely automatically from the individual operations in your network. So most deep learning frameworks will just do it for you. This is called backpropagation, and it's a very powerful concept.
And remember, he says individual derivatives can be computed, and this is what the Hogwild algorithm does, right? It can parallelize all of this.
It makes computing derivatives of complex functions very efficient, as long as the function is made out of simple blocks with simple derivatives. Running the model up to the predictions is often called the forward prop, and the model that goes backwards is called the back prop. So to recap, to run stochastic gradient descent, for every single little batch of your data in your training set, you're going to run the forward prop and then the back prop, and that will give you gradients for each of your weights in your model. Then you're going to apply those gradients with the learning rates to your original weights and update them. And you're going to repeat that all over again many, many times. This is how your entire model gets optimized. I'm not going to go through more of the math of what's going on in each of those blocks, because again, you don't typically have to worry about that, and it's essentially the chain rule. But keep in mind this diagram. In particular, each block of the back prop often takes about twice the memory that's needed for the forward prop, and twice the compute. That's important when you want to size your model and fit it in memory, for example.
Okay, so that's it. That's what deep learning is. This is the basic concept of deep learning. And this back propagation was not, discovered or invented when neural networks were first introduced. So when back propagation was brought in, that's when there was a big wave and there was a big, there was big hype around artificial neural networks. And then it went down because there was not sufficient data and there were not sufficient computational resources. But now with distributed computing frameworks and the availability of large data and big data systems, it's come back. Okay. And right. The important step we missed, or one of the steps we missed, is the step size. How do you calculate the step size? Okay. H2O AI does this automatically for you. And uses an algorithm called the ADA delta, right? So this is a paper on ADA delta. If you're interested, you can go through this, and they talk about how they set the learning rate. So this is adaptive. Again, it's not fixed. They adapt this based on data. Okay. This is written by somebody in Google. This paper also is about adaptive learning rate. This is also written by somebody else from Google, but H2O AI uses ADA delta to set its step size. Okay. So all that we saw right now is fully connected neural networks. Now we'll go to another flavor of neural networks called the convolutional neural networks. And it looks something like this. So as you see here, the blue ones, the blue balls, like blue circles, this is the input layer, okay? The green one is the first hidden layer, the blue is the second hidden layer, and F is, let's say, the output, this orange one, okay? And the connections you see to this green layer are from adjacent circles, okay? So if you imagine this input layer as an image, okay, what it is doing is adjacent pixels, okay, are given as input to the first hidden layer, and so on to the next layer as well. So why this works is because, let's say you have a picture, a two-dimensional picture, and you want to identify an edge, okay? So the information to identify the edge, let's say at the bottom left corner, you just need pixels from the neighborhood of the bottom left corner, and you don't need any other pixels in the image to identify that there's an edge at this particular location, okay? So that is why only the pixels that are close by are connected to the next layer. And this also reflects the way in which your eye works. So the neurons in your eyes are also connected in a similar manner, okay? The advantage of doing this is that we have massively reduced the number of parameters that we want to learn, because instead of a fully connected network, this is now much smaller. Okay, the number of parameters that you have to learn are much smaller. Okay, and the other big advantage of this is it also takes into account the spatial alignment of different pixels, right? Because this is a 2D image and the input you see is two-dimensional. Right? So it also preserves the spatial information that you get from the image. Whereas if you flatten it out like this, you know, if you flatten it out like this, you don't have this, you are sacrificing the spatial information, okay? And there's a strange optimization that is also done here, which is, let's say this edge you see here, okay, this left edge from A to B, okay, the weight on this is the same as the weight that goes from this edge to this one. Okay, all the left edges will have the same weight, and the same way this one as well. And all the right side edges will have the same weight, and all the edges that come from the back, let's say this one, will also have the same weights. So this also massively reduces the amount of, or the number of parameters that you want to learn. And I haven't been able to understand why this works, but it works. So
that kind of trick is standard in some sense, right? Because what it's, so the idea is that you're assuming that the parameters are the same for a given, a given scanning region, right? So then, so in probabilistic models, these kinds of things can be justified by what's called Markov property. So you're saying that only the local, there's only local dependence, and the way the local dependence works is identical across different regions. It's an assumption, but it's not a natural one.
Right.
So it reduces dimensionality, but it seems to work.
Yes. Yep. So yeah, maybe what happens is we are sacrificing a really small amount of accuracy for computational efficiency. Maybe, I don't know, but yeah, it works, and there are lots of papers that justify all of this. So I haven't read them. Okay, and this is some convolutional neural network in more detail.
Let's talk about convolutional networks, or ConVNets. ConVNets are neural networks that share their parameters across space. Imagine you have an image.
So that's what it is. Share across space, meaning all the left ones are same, right? So across space, it's the same. That's what it means.
It can be represented as a flat pancake. It has a width, a height, and because it typically has red, green, and blue channels, it also has a depth. In this instance, depth is 3. That's your input. Now imagine taking a small patch of this image and running a tiny neural network on it. We say K outputs. Let's represent those outputs vertically in a tiny column like this. Now let's slide that little neural network across the image without changing the weights. Just slide across and vertically like we're painting it with a brush. On the output, we've drawn another image. It's got a different width, a different height, and more importantly, it's got a different depth. Instead of just RG and D, now you have an output that's got many color channels, K of them. This operation is called a convolution. If your patch size were the size of the whole image, it would be no different than a regular layer of a neural network. But because we have this small patch instead, we have many fewer weights, and they are shared across space. A convnet is going to basically be a deep network where instead of having stacks of matrix multiply layers, we're going to have stacks of convolutions. The general idea is that they will form a pyramid. At the bottom, you have this big image that's very shallow, just R, G, and B. You're going to apply convolutions that are going to progressively squeeze the spatial dimensions while increasing the depth, which corresponds roughly to the semantic complexity of your representation. At the top, you can put your classifier. You have a representation where all the spatial information has been squeezed out and only parameters that map to content of the image remain. So that's the general idea. If you're going to implement this, there are lots of little details to get right. And
so I'll stop this here because he goes on about introducing other terms like patch and stride and those things which you don't need. Okay, so that's what your convolutional neural network does. It, what he means by the stride moving across the image is the next layer. So from this layer, we get this layer, and we choose this K. Right, okay, so in this case, in our case, K is 4. Okay, so 4 inputs are fed to the next layer. Okay, and this image is taken from this blog. Okay, and this is a really good explanation of convolutional neural networks. So he goes in depth about what each layer is doing and what these connections mean and all of that. Okay, so go through this blog. And convolutional neural networks have become really popular these days after a paper by Alex Krzyzewski, Jeffrey Hinton, and Ilya Sutskever. So these are the guys who introduced ReLUs. They introduced dropouts, and they introduced convolutional. I think they, I don't know if they introduced, but they use convolutional neural networks. And this is the network that they came up with. And what they do is they do classification on a set of data called ImageNet, which is full images with pictures of dogs and cats and all of these. So I think there are 10 categories of images. So and this is the most accurate classification that's been done on those sets of images. Okay. Right. So this was quite a big landmark paper, which was done in 2012, and yeah. Now, convolutional neural networks, we saw share parameters across space. That's what these things are, right? So across space, we're sharing parameters. What recurrent neural networks do is they share parameters across time. Okay. So why time? Let's say we are doing some kind of speech processing or text processing. So we get new words as we read through the document, right? Or we get new sounds or new voices as we go through an audio clip or something. So across space, parameters are shared by this recurrent neural network. Okay. And this is how it looks. So I'll play this video.
You've already seen how a convolutional network uses shared parameters across space to extract patterns over an image. Now you're going to do the same thing, but over time instead of space. This is the idea behind recurrent neural networks. Imagine that you have a sequence of events. At each point in time, you want to make a decision about what's happened so far in the sequence. Imagine that you have a sequence of events. At each point in time, you want to make a decision about what's happened so far in the sequence. If your sequence is reasonably stationary, you can use the same classifier at each point in time. That simplifies things a lot already. But since this is a sequence, you also want to take into account the past, everything that happened before that point. One natural thing to do here is to use the state of the previous classifier as a summary of what happened before, recursively. Now, you would need a very deep neural network to remember far in the past. Imagine that this sequence could have hundreds, thousands of steps. It would basically mean to have a deep network with hundreds or thousands of layers. But instead, we're going to use tiling again and have a single model responsible for summarizing the past and providing that information to your classifier. What you end up with is a network with a relatively simple repeating pattern, with part of your classifier connecting to the input at each time step, and another part called the recurrent connection connecting you to the past at each step.
Okay. So what you do is you have the parameters which are connected to the node itself. Okay, it's like this, Okay, and when you unwrap it, this is what it becomes, which is what was shown in this diagram. Now the problem with recurrent neural networks is there are two problems. One is the derivative. The derivative, one, it quickly goes to infinity or it can go to zero. Okay. So to solve these two problems, there are two approaches that are taken to stop it from going to infinity. What we do is we have a max cap. So if the derivative goes beyond that, you just stop computing the derivative. And if it goes to zero, we have two techniques, or a variation of one technique, which is called long short-term memory. And it looks something like this. So don't worry about all this complicated thing. So this tan H is essentially our ReLU, okay? And all these sigmas, these are nothing but the decision of how far back in the past you want to remember. So it's like a memory cell saying, okay, given this new input, should I remember all that I've remembered so far, or should I truncate it to some point? Okay. So it's like saying, let's say, most people in France speak dash, okay? So let's say there are some sets of sentences before these sets of words. You know that to predict the next word, which is French, right? All you need is France, right? Most people in France, okay? You don't need sentences before that. So that's what these cells do. So to understand it, that's what these things do. Okay. But this again requires a lot of memory, and to optimize that, they've come up with something called the gated recurrent unit, and it looks slightly more complicated, but you can get more details from this paper. Okay. So the difference between this and this is that this function, right? This to decide whether, so the difference is that this layer here is open. So in this, there's nothing open. You always have to go through the sigma. Here it's open, one input is open. That's the difference. Okay. And with this, they save a lot of memory. I don't know the details, but yeah, it's available on this paper. Okay. So far we have talked about supervised learning techniques, where we did all kinds of classification and different variants of neural networks that help you better classify images and text and speech. Finally, let's go to AutoEncoders, which are a technique, which are neural networks again, but you can use them for unsupervised learning, and more specifically for anomaly detection. Right? And the way we do this is by squeezing the inputs. So you see each hidden layer here, all of these are hidden layers except for the output, of course. Each hidden layer is getting squeezed. So it's actually, what it is doing is it's only deriving the essential information from each of the input layers, and subsequent layers learn more and more abstract information about the input. And once we do this, we try to reconstruct the same input by expanding out the layers. Okay. So what the idea is that when you're squeezing information, it only preserves the essential information about the input. So the outliers or the input, input points, which are not normal or which are not similar to the other ones, they will not be able to be accurately recreated by the output layer. That's the simple idea here. So you take the input, you try to learn only the essential information from the input, and then using this essential information, you're trying to recreate the output, and the output can only show the normal points. Okay, so the abnormal ones are lost. That's what AutoEncoder is. And I will not play this video. This video I found on YouTube. It's not from Vincent's course, but yeah, this is a good explanation of AutoEncoders. Okay, so that's it for deep learning. I'll go next to an introduction to sparkling water.
So your introduction to deep learning basically is a overview of Vincent's course, right?
Yes.
This is what? How many hours do you need approximately to properly do that?
Yeah, the recommended time to do that is 3 months, including all of the exercises. But I skipped doing all the exercises, and it took me 3 or 4 days, I think.
Okay.
Yeah.
But by going through the lectures and
yes. Yes. Yeah. Went through all the lectures. And
so what's the purpose of an AutoEncoder? Because, yeah, I mean, what's the purpose of it? Why do you use that?
Yeah, autoencoders are used for anomaly detection.
Anomaly detection?
Yeah.
So it's like trying to reduce the dimensionality of a thing.
Yes.
In order to see what's different in the output. And
yeah.
then you compare the output with the...
Yes. So what the output is trying to do is to recreate the inputs based on this abstract representation, let's call it. Okay. Yeah, that's yeah.
So, yeah, and my last question is, so if you have to summarize, I mean, in one sentence, what's the difference between the classical neural networks and the convolutional neural networks?
Mm-hmm.
What would you say? I mean, I could say it by myself and then you try to correct me. But what I understood is that in convolutional neural networks, you have to reduce by yourself the size of the hidden layers. Yeah, in the normal ones, the hidden layers are the same size.
Mm-hmm.
In the convolutional ones, you reduce them in purpose. So,
okay.
Yeah, but which are the other additional changes between the normal ones and the convolutional?
Right. So we actually don't need to have the hidden layers of the same size, even in a fully connected network. The difference with convolutional neural networks is because it needs to learn far fewer number of parameters. It's easier to tune, easier to train, right? And the next is because it uses the locality of information, it's more optimal.
So it's in the way in which the inputs are connected to the units inside the layer.
Mm-hmm.
So most than the structure the network provides.
Yes, yes. It's trying to use the spatial information or the locality actually. Yeah.
Okay.
Yep. Okay, so the library or the framework that we're going to use to try this is called H2O AI, and this is what H2O AI is. Just an overview of H2O AI, the features that it has. Ignore this thing for now. So it can run on Windows, Mac, and Linux. It has language bindings to Java, Scala, R, Python, and it also has a REST API. It can run on top of the big data frameworks and the Hadoop distributions like Cloudera, MapR, Hortonworks, and on Spark. It can run on the cloud computing environments. And because it has a REST API, it can run on your browser itself. So they give you a UI which you can run on the browser, and you can tune all your parameters, and you can choose your algorithm, and you can just run it on a data set. Okay, so it's quite good. And it's written in Java and Scala. Okay, so the main concepts for H2O are something called the H2O core. So this is the core computation and distributed processing engine. And H2O flow, this is the UI bit. They also have a lot of, I think 6 or 7 algorithms that they've implemented. H2O flow, I don't know what's H2O flow. Yeah, H2O flow is the UI. Yep, sparkling water is H2O connector that runs on top of Spark. So it's a component that helps you run H2O jobs on top of Spark. Okay, and H2O frame is their data structure, like RDDs in Spark. You know, just as RDDs are an abstraction for all the data structures that you can, not all the data structure, let's say the distributed data structure in Spark. In a similar way, H2O frame is the data structure that is used in, H2O frame is the data structure used in H2O. Okay, so this is the architecture diagram of H2O. You can go through this link for more details. They implement machine learning algorithms using MapReduce. So they still use MapReduce, but because it can run on top of Spark, MapReduce can be distributed and it can be in memory, right? And the algorithms, like I said, are implemented in Scala. You can implement your own algorithm as well. These are some of the algorithms they have: deep learning, k-means, PCA, GLMs, right? They also have a good parsing module, so you can just feed in your data, set up some parameters on the UI, and it will do the ETL for you. So we don't need to spend a lot of time doing ETL. Okay, and it can run on top of Spark, Hadoop, or by itself. So this video is about H2O flow. I'm not going to play this. So as you can see, you can draw some nice graphs and all of this stuff just on the UI. You don't need to write any code to get all of these things done. Okay. So go through these links for tutorials on the different algorithms and references. Okay. And this is how sparkling water works. On each Spark executor, H2O node runs on top of that. Okay, and what you do is, from the driver node, we know that we submit jobs using the Spark context. In the Spark context, you also inside your driver, you also initialize the H2O context, and you submit jobs to the H2O context, and this submits job to the H2O nodes, which are running on top of Spark executors. Okay, so it uses a similar model as Spark. Okay. So because it can run on top of Spark, it's agnostic to the cluster manager used by Spark. So it could be Spark standalone, or Yarn or Mesos or anything, right? And like I said before, the data structure that it uses is called H2O frame. The question that immediately we get is, what if we use H2O frame? Does our data from RDD or data frame, does it get duplicated when we use the H2O frame? So the answer is, this happens in one direction. So if you have data that's in a Spark RDD or a Spark data frame, and you're creating a H2O frame from that, your data will actually get copied, so it will get duplicated. But on the other direction, from H2O frame, if you want to read data as an RDD, or you want to perform some kind of RDD operations on top of H2O frame structures, then data is not copied. So H2O frame has an implicit conversion to RDD, and so it doesn't duplicate any data. So it supports all of the functions that you need for RDDs. Okay. So these are some of the documents for H2O. The documentation is, I wouldn't say very good. They have a lot of documents, but it's not very well organized. So go through you can go through the documents, and this is a good PDF that I found, which talks about deep learning implemented in H2O AI in depth. And this is where I found that they use Hogwild and they use ADA Delta and all these things. So you can see this much more in depth. So, yep. So go through this booklet. Right. So let's go to an example. So this example is reworked from this example published in H2O Sparkling Water. Right, so it's on GitHub. So I started off using the example in Databricks guide, but yeah, it was meant for an older version of H2O AI, so I had to rework that example, and then I took this example and I converted it from using. So this was using the old MLlib library, so I converted this to use the ML library. Okay. So what we are going to do in this is a simple spam classification of SMS data. Okay, so the steps we are going to do are just to explore the data set, extract the features, and for featureization, we're going to tokenize the words, remove stop words, do hashing, and build a TF-IDF model. Then we are going to train the deep learning model. So we've done all the featureization steps here. So we train the deep learning model, and finally we predict using our model. Okay. So this data, the ham spam data, is already available on Databricks. Okay. So my notebook is not attached to a cluster, so I'll attach it to this one. So one thing to remember when running H2O AI on Spark is that on Spark Databricks is that you need at least 3 nodes for this to run. So you need at least 3 worker nodes, otherwise this doesn't run. Okay, so it's quite memory hungry and power hungry. Okay. Okay, so this is the data set. Yeah, so the data set is already available in Databricks file system. If it's not available, you can use this little code snippet to get the data. This again, I have taken it from Sparkling Water's GitHub. Okay. So let's look at the data. Right, so if you see here, the data is separated by tab. Okay, so ham is the label, and then there's a tab, and then there is actual text. Okay, and this is another label, and there's a tab space, and there's some other text. Okay, so as before, we'll just convert our data to a data frame using the Spark CSV reader, and then we are separating it using the tab delimiter. Okay, and our data frame has 2 columns now: ham or spam, the label, and the message. Okay, so this is a tiny data set. It only has 1,300 messages. Okay, so we'll just display the distribution. It's 25% spam and 75% of the data is ham. Okay, so let's get to tokenization now. We have seen the regex tokenizer before. I'll just run this. So we are splitting by white space. and we're dropping words which are less than 2 characters in length. And we're also lowercasing it. This we have done before. Now we're going to remove the stop words. The stop words, remember, we did it in one of the previous classes. It's already available in this location. So I'll take that file which has all these stop words, and I'm going to add a few more, like comma and colon and semicolon. So you can see all the stop words here. And the source of these stop words is this particular URL. Okay, so it's taken from this particular URL. Now I'm going to remove all the stop words. Okay, and then we're going to hash the words using hashing TF. So this is what we're going to do is we are going to create a hash of 1024. An array of 1024 hashes. So what we're trying to do is we're trying to convert each word into its frequency, right? So this hashing TF, what it does is it assigns a frequency to each of the input words. Okay. So we have done that, and then let's just print the schema. So our data frame has the label, it has the message, and then we converted the message into tokens. We filtered the tokens using the stop words, and then we did this hashing. Okay, so I'll just print this. So this is the label, this is the message, and this is what our hashing hashed data structure looks like. So this is actually nothing but a sparse vector. So 0, 1, 0, 2, 4 is the size of our vector. These are the indices at which there is some value, and the value or the frequency is 1. Okay, so some words. Then we do this TF-IDF. TF-IDF tells you how important a word is. Okay, so let's say you have a set of documents and you want to classify those documents. And let's say in one of the documents you get a word like retinopathy. Okay, this is a word used by Vincent in his lecture as well. So when you see the word retinopathy, you know that it's something to do with the retina and the eye, and pathy is like pathology or some disease. Right? So this particular word is a strong indicator that that particular document in which it occurs is a medical document. Right? Instead of, let's say, just the word retina, which could mean the retina in your eye, or it could be retina display of monitors. Right? So certain words have more weight towards helping you classify that particular document. So TF-IDF makes use of that. So less frequently occurring words are a strong indicator of the class of a document. Okay? And that's what your TF-IDF does. So remember, so far we have done ML transformations. So these are all not materialized. Okay, these are not materialized. But when we want to do a TF-IDF, because it has to go through every single word in the whole corpus, it has to be materialized. And that's why you see here we do a fit. Okay. So let's just display this. So this is, as we have seen before, is the hashing frequency. And this is the TF-IDF. Okay, for the same indices, 132, 140. These values are the frequency of those terms, inverse frequency. Okay.
So this is term frequency, inverse document frequency.
Yeah. Okay, I've put this. Okay. Yeah. Right. So this function is nothing but, I just put all of these things together. So tokenize remove stop words hash. I just put all of these things together in a helper function. Okay. Now this is the part where we are attaching H2O library. Okay. So we have imported H2O and then we are creating a H2O context. H2O has really good logging, I must say. You see, it will tell you all the nodes to which it's attached and all of that stuff. So let's wait for this command to finish. Okay, while it's running. So I tried logging in using the browser to go to this URL, but it doesn't work because this particular port needs to be unblocked in AWS. Okay, otherwise it won't work. Right. So we need to wait for this to finish twice. Okay, let me try canceling it and running it again. Let's run it again. Okay, let's pass this time. Okay, so all we need for our model is the label and the features. This features is the TF-IDF features. Okay. So what we are doing is from the TF-IDF data frame, we are selecting just the label and the features and converting it to a H2O frame. And this is done through Scala implicits using the H2O context implicits. Okay, so it's converted the features into H2O frame. So you can see here. So you can see the TF-IDF values here. Okay. And now what we're doing is in this step, we are replacing the label with a categorical value because ham or spam is a category value, right? Whether it's ham or spam, there's just only two possible values. So H2O frame has this helper function called toCategoricalVal, and we're just using this to convert our labels to category values. Okay. In this step, what we're doing is we are splitting the data into training and test data sets. So, yep, we take a sample of 0.8, so 80% of data is training, and the remaining 20% is the test data. Okay. Now there's a question of what. Yep. So once we get the training and test data sets, we set the parameters to our model. So we can set that using deep learning parameters class. So this is the training data set, the test or validation data set. So your deep learning model in H2O frame can also perform cross-validation and foldings and all of that. So we can just set this here. And this is the activation function or the nonlinear function that we saw. It's a rectifier with dropout. So rectifier is the ReLU, and dropout, I'll show you what dropout is. And the response column is ham or spam. So once it trains, and when we try to predict it, the output will be set in this column called ham or spam. Okay. Epochs is the number of times it runs, like the number of trainings. This L1 is the L1 regularization. This is the important parameter hidden. This will help you set the number of hidden layers and the size of each hidden layer. So we have 2 layers, and each layer is of size 200. Okay.
So is the number of steps the only step criteria that you have? So you can.
Yeah, you can set all of that here. Oh, this is not the one. this is not the one.
If we go to the deep learning, yeah.
Oh yeah, sorry. Yeah, you can set all of these hidden layers, epochs, importance of variables, folding, weights, you know, yeah, lot of parameters. Right. Stopping rounds. Actually, if you use the UI that they have, the H2O water, you can set all these parameters in their text boxes. And when you say train, it will start training. And you can pause it in the middle. And you can reset some values. Like you can change L1, L2 regularization, for instance. And then you can continue training. So you can see how the model is performing as it's being trained. And you can tune the parameters on the go. And you can do this because of back propagation, right? So it'll, yeah. So, but you cannot do that when you're writing code because you cannot. So all you need, so what you need is a handle to the object that's running, right? So you can't do that with code. But I'm sure you can do that because it's open source. So probably go and hack together something. I'm sure it'll work, but they haven't provided an open API to do that. Okay. So I'll run this. The last time I ran this, it took 52 seconds, as you see here. So it'll take a while. So while this is running, I'll play this video on dropouts.
There is another important technique for regularization that only emerged relatively recently and works amazingly well. It also looks insane the first time you see it, so bear with me. It's called dropout. Dropout works like this. Imagine that you have one layer that connects to another layer. The values that go from one layer to the next are often called activations. Now take those activations and randomly, for every example you train your network on, set half of them to 0. Completely randomly, you basically take half of the data that's flowing through your network and just destroy it, and then randomly again. If that doesn't sound crazy to you, then you might qualify to become a student of Jeffrey Hinton, who pioneered the technique. So what happens with dropout? Your network can never rely on any given activation to be present, because they might be squashed at any given moment. So it is forced to learn a redundant representation for everything to make sure that at least some of the information remains. It's like a game of whack-a-mole. One activation gets smashed, but there is always one or more that do the same job and that don't get killed. So everything remains fine at the end. Forcing your network to learn redundant representations might sound very inefficient. But in practice, it makes things more robust and prevents overfitting. It also makes your network act as if taking the consensus over an ensemble of networks, which is always a good way to improve performance. Dropout is one of the most important techniques to emerge in the last few years. If dropout doesn't work for you, you should probably be using a bigger network.
Okay. So the first time I saw it, it was quite, yeah. Okay, this trained in 26 seconds, so it's faster than last time I ran it. And actually, if you see, again, the logging is really good. It'll tell you parameters like mean square error, area under the curve. You know, see, area under the curve is 0.9998, which is very, very good, right? Okay, so the same thing, let's see these metrics for training. So the training metrics, as you see, is like very impressive. But when you look at the validation metrics, these are not bad at all. 9.9974, it's not bad at all. It's, you can easily compare it with the training metrics, so it's quite good. So the hyperparameters we have chosen are good, right? So now let's do a prediction. This is just a helper function that helps you predict, okay? And okay, so spam true. So we try to contact you, blah, 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 and it says that it's spam. So model thinks it's spam. So yeah, this is a legitimate message, and that's what our model thinks as well. Okay. Let's see some other one. Okay, this again.
So the featureization basically involved removing stop words and
Yes.
then doing TF-IDF.
Yes, correct.
Yeah,
That's it.
basically it.
Yep.
Right?
Yep.
All right.
Yeah, just yeah. The thing with H2O is that you can only do fully connected neural networks. It doesn't have support for convolutional or recurrent neural networks. So yeah, that's one thing to keep in mind if you're using this. But Raz is going to talk about TensorFlow. I think TensorFlow has support for both of these other types of neural networks.
So since we're running out of time, I'm going to just zip through TensorFlow in a hurry, and then I'll let you guys read about TensorFlow on your own. So with TensorFlow, we need to first set up the Spark cluster, right? Because TensorFlow is in Python. It's Google's library. We will watch a quick video about it. And then you need to set up the Spark cluster for TensorFlow. Okay, here are some initialization scripts. So we won't actually do the full setup this time. And we'll just look at a pre-run analysis quickly. So this example is taking the TensorFlow library in Python and using it in a sort of fault-tolerant, embarrassingly parallel way in Spark, where we take the trained model and broadcast it to all the different nodes, and then use Spark for just prediction, basically. Right? So this can be quite helpful, and if you want to actually train a TensorFlow model from scratch for a particular application, then you can do that as well. But okay, so let me. So yes, so once you've installed it, these are just scripts to testing it. Here, our main job is we're going to download a model that's sort of pre-trained by Google already. And this model was trained on a very, very large corpus of image data. And what this model does is it will pick out non-human objects from images, right? So what we're showing here is you could download a pre-trained model and distribute it into your Spark nodes. And then you can have a whole list of images that are coming at you, and you can do predictions with the pre-trained model and serve these predictions back to the client. That's kind of the setup. So here is actually a lot of the work you need to do to download the model.
So how long does it take to train that model?
So this was trained by Google already, and it's sort of available for anyone to download. And there are various models that are pre-trained by Google, which I don't know how long this one took, but it's a lot more than.
There is a blog that describes the steps that they've done.
Yeah.
And it also has code for training your own model. So maybe run it on the DataBricks clusters.
Yeah. So so let's actually just do a tiny bit of. So TensorFlow is actually a really nice library that Google open sourced recently, right? So what is TensorFlow? Let's just sort of quickly dive into this for a second.
Deep learning is a branch of machine learning loosely inspired by how the brain works. We have had experience building software for deep learning in the last few years. Although it was initially a research project, we've since collaborated with about 50 different teams at Google and deployed these systems in real products across a really wide spectrum of areas. Today, it's used heavily in our speech recognition systems, in the new Google Photos product, Gmail, in search. We've really taken all that experience and built that into TensorFlow. TensorFlow is this machine learning library that's used across Google for applying deep learning to a lot of different areas, doing both artificial intelligence research and deploying these production models. They're really powerful at doing various kinds of perceptual and language understanding tasks. These models are able to actually make it so computers can actually see. They're actually able to understand what is in an image when you're looking at it, what is in a short video clip. And that enables all kinds of powerful products. Machine learning is the secret sauce for the products of tomorrow.
It no longer makes sense to have separate tools for researchers doing machine learning and people who are developing real products. There should really be one set of tools that researchers can use to try out their crazy ideas, and if those ideas work, they can move them directly into products without having to rewrite them.
On the research side, the goal is to bring new understanding to existing problems, advance the state of the art on existing problems, understand new problems that weren't considered before. But on the engineering side, the goal is to take those insights from the research community and use them to enable products and product features that wouldn't have been possible before.
Part of the point of TensorFlow is to allow collaboration and communication between researchers. It allows a researcher in one location to develop an idea and explore it, and then just send code that someone else can use on the other side of the world.
We are making it a lot easier for humans to be able to use the devices around them. We think having this as an open source tool really helps that and speeds that effort up. So we expect developers to be able to do a lot more than they can do today.
We think we have the best machine learning infrastructure in the world, and we have the opportunity to share that, and that's what we want to do here.
Okay, so I know this is kind of a commercial thing, but there is a whole lot of work behind this. So it's a lot better to use Google's TensorFlow than to create your own, roll your own library, or use some academic library that has very little support. So that's the motivation for this, basically. Since we're running out of time, I'm basically going to jump very quickly down to the application. So we've downloaded this model that was pre-trained by Google, and it's a very, very big model, actually. I think it's 250 megabytes. So this is after the training was done. There is this model you can download in the standard model format, and it's about 250 MB. Now, the amazing thing with this model is you can serve images to it, and it'll pick out objects and tell you what they are, right? Which is kind of cool, actually. So one natural application will be to take pre-trained models like this and put it into robots and say the agricultural field around Canterbury. These robots should be able to recognize fruits, different kinds of fruits at different levels of ripeness, and they can, assign these probabilities. So you can have drones or robots go and scout out what fruits are ready for picking, for example, very simply. And the beauty here is you do all the training in the cloud, and then you just dump 250 MB of the model into the robot, right? So a drone can easily have that much memory capacity, for example. So that's the kind of thing you can do with TensorFlow. So here what we've done is basically have about 100 and some images that we've sort of picked up from the web. And then we're pointing to this URL for this image, and then just showing this image, right? So this is Grace Hopper, one of the famous women in computer science, sort of behind high-level languages. So, and then if you basically pass that URL into the model we downloaded that has been broadcast into all the Spark nodes, then it basically picks up the objects as the 0.808 probability. It's a military uniform, and 0.02, it's a suit of clothes. It's pretty good. I don't know what this is, pickle hob. It's very low probability. So it's able to do these predictions of objects. So now remember that the model that's been trained actually has lots and lots of categories, right? This is basically the final most layer that came out of the convolutional neural net with all the categories. So the categories will include military uniforms, suits, and microphones, and cuttlefish, and all kinds of things. So you'll see here, there's another example. We just loaded a different image, number 5, and then so we just basically ask what the tags are, and it picks up it's a stage, and it's a microphone or a mic, and pretty good. Okay. And then this is another example, which is underwater scene, and then we can ask what it is, and it's saying it's a wreck. It's picked up, it's a shipwreck. That's pretty cool. A scuba diver, coral reef, and so on. So that's the kind of thing, this is sort of fault-tolerant, embarrassingly parallel broadcast of a pre-trained model in Spark, so you can do very quick serving. But of course, by doing the Udacity course and understanding the theory properly, you can actually start training your own models using TensorFlow. And that's essentially what we would like you to do. Okay, so thank you very much. And if there are no questions, we will call it a day.